A negative charge Q is distributed uniformly on the surface of a balloon, a radius r. Oh yeah, I guess they do small r. Clever. The balloon is isolated, and then, okay, isolated from the charge source probably. That way, what they're saying here is that the charge stays the same. Q is constant because they put the charge on the balloon, isolate it. Now when it gets bigger and smaller, the charge can't escape. So the charge density might lower because the surface area gets bigger, but the number of charges stay the same. That's what they mean by isolated. And then inflated to a larger radius r, clever, big R. Man, if I wrote this test, I probably would have switched the r's just to make life people hard and just be completely difficult without any net benefit. Nah, I probably would. Maybe I would. I don't know. Focus. What is the relationship between the final values of the magnitude, absolute value, of the electric field at the surface E, the potential at the surface, and the electrostatic potential energy of the balloon relative to their energy value, initial values? Okay. So we're going to start by looking at the electric field. So the electric field, Gauss's law, integral E dot dA, this is a dot product where the area vector is the normal to the surface, Q enclosed over epsilon naught. So at the surface, to do this, we basically, for the Gaussian surface, we would draw the surface right at R. So this would be 4 pi r squared here for the initial I guess balloon, the deflated balloon, less inflated. But when we do this, when we look at it for the big one, we're going to use a bigger Gaussian surface, so 4 pi big R squared. Long story short, when we solve that, we get E is going to be KQ over R squared. R squared for the small one, R squared for the big one. And since R goes up, the electric field is going to go down because R is in the denominator. So the magnitude of the electric field is going to be smaller. And so another way to think of this is you can model the electric field of a sphere as the electric field of a point charge. I'm going to draw these electric fields going in because it's negative. And the strength of the electric field, I know I should do an infinite number of these and they should all be uniform. They're not. The electric field strength is going to be related to how densely packed the arrows are. So this is small r, that is big R. You can say there'd be a higher density of arrows for the smaller r, lower density of arrows for the bigger r. Therefore, the magnitude of the electric field is going to go down lower. So we'll have smaller. So now we want to look at potential. So potential, we can look at that in the same way. So voltage, there's different ways of defining voltage. So what I'm going to use is E equals E dot dr. When we do that integral using KQ over R squared, we get KQ over R is the voltage. So the voltage for little r is going to be KQ over R. Voltage for big R is going to be KQ, because we have the same charge, over big R. And both of these are going to be less than 0 because Q is less than 0. So as R goes bigger, the magnitude of the voltage goes down. But what that means, since it's negative, is it's getting closer to zero. So if we do like a number line, this is 0, this would be voltage big R, this would be voltage small r. So voltage big R is actually going to be larger. Let's see, smaller, higher. So it's going to be this one. Yes. So, oh, that's the only one we have to do. So no, same. Nope. Up. Nice. So we know it's going to be this one. So the voltage actually gets higher, but it's still negative, which makes it intuitive. So the magnitude gets smaller, the value gets higher, and that's kind of tricky, and it's easy to talk yourself in circles because electric fields are vectors, magnitude and direction. Potential is voltage, which is a scalar, but even though scalar doesn't have direction, it does have positive and negative, usually sometimes depending on who you're talking to. So therefore, you do have to do the positive negative thing. And then potential energy. There's different ways of thinking about potential energy. One way you can think of it is V equals Q times U. But energy is usually thought of as a magnitude and not a so voltage potential usually has positive and negative, but you usually don't think of positive and negative in terms of energy, at least not in this way. So the easier way to think of this for energy is there's a formula for energy, and that is, I think it's 1/2 epsilon naught E squared. I should probably look that up real quick just so I don't go too far astray. Potential energy in terms of electric field. And yes, true. I think so. Mostly true. I'm going to go with true here. Anyway, the relationship I care about here is relationship to electric field. Oh, and this is the electric field density. So it's per unit volume, not total. So this is per unit this electric field density. This is the potential energy density. So it's the energy due to an electric field due to electric field squared. Long story short, more electric field, more potential energy. And so what we're going to look at here is the electric there. If we look at our two circles, I know I already drew on the other ones too much. We have the first one, we have the second one. They both have effectively the same electric field coming from the center. It's just that as soon as you get within the circle, the electric field disappears. Gauss's law, Q enclosed is 0 within the sphere. And so what that means is that there's this portion of this electric field, so basically from the small circle out, which we have on the first situation, but we're now missing in the second scenario. And so that absence of the electric field is going to effectively be energy we don't have. And by not having that energy anymore, we lost it. Therefore, our total energy due to the electric field is now lower. So the answer for this one would be D. The electric field goes, the magnitude of the electric field goes down. The electric potential is higher because you have a negative value with the magnitude getting smaller, meaning it's going closer to 0, and the voltage is actually rising. And then the potential energy is lower because we're basically truncating a portion of the electric field. And when we lose that electric field, we lose the energy associated with it. So I know that there's probably quicker, easier shortcuts on doing this. These questions are very conceptual, and it's really easy to miss multiple choice. So I try and think about them as methodically as possible. So I hope that helped. See you next time.